Hello, everyone. My name is Gary Klein with Gary Klein and Associates. I'll be the moderator for today's session on right-sizing equipment and piping. We'll start this webcast with a few announcements and then move on to our presentations. First and foremost, I want to thank all of our sponsors and ACEEE Ally members for the support of the Hot Water Forum and ACEEE. Please use the chat box on the right-hand side of your screen to ask questions of the presenters. As moderator, I'll gather all the questions and share for the presenters to answer once all the presentations are complete. If we don't get to your question, please join us for 20 minutes of chat and discussion on the Zoom platform immediately following the session. The Zoom link is posted on the audience screen. Please refrain from using the chat for any dialogue other than asking questions. Please note that there are two kinds of questions, clarifying and exploratory. Clarifying questions, I'll do my best to get to the presenter in real time. For exploratory questions, we'll handle later on in the at the end of the presentation or during the Zoom period. Please be sure to check out all the tabs on the left-hand side of the app. From there, you can network with attendees and other program participants, visit sponsor pages, and engage in our game to possibly win a free registration to the 2023 Hot Water Forum in Mission Hills, California. The resources section includes a program and the list of attendees for downloading. Lastly, we ask everyone to help plan on our planning of the future Hot Water Forums by completing the conference evaluation. Anyone who completes the evaluation and includes a testimonial will receive a $25 discount off their 2023 Hot Water Forum registration. All presentations will be available for on-demand viewing to registered attendees on the platform within a few days and will remain available for viewing until May. Presenter slides can be found on their page in the program participants section. And now I'd like to introduce our distinguished panel of speakers. We have Bob Barrett with Bob Barrett Consulting, Peter Skinner from E2G Solar, and Todd Kupta with J.M. McClenahan. All of them have very interesting presentations for us today related to hot water systems and right-sizing the plumbing. And we're going to start with Bob Barrett. At least that's my plan. There we go. Bob, I see you are here. Are you ready?
I'm ready.
Cool. I'm going to go on mute and I'll be back when I need to.
Okay. All right. Well, thank you. So we're going to talk about domestic hot water theory versus reality today. Let's see if this slide advances good. All right. So the problem is it's difficult to calculate domestic hot water loads. The unknown items include occupancy, which varies based on location and demographics, entering water temperature, which can vary from 40 to 75 degrees, fixture usage temperature, which can vary between 105 and 120, depending on the fixture being used, the diversity of usage, which is flow based on the type of fixtures and the quantity in use, usage time per fixture, which varies from person to person and season to season. An example would be showers, right? In the Northeast, we're going to take longer, warmer showers in the winter than we are in the summertime. Peak duration and size, which varies from building to building. That's essentially, your peaks and your valleys within your demand. So what is an engineer to do when they're missing key pieces of information, when missing the mark could result in a lawsuit, and when nobody, including the engineer themselves, will know if they overestimate the load? Well, you oversize, of course. And that's what we see time and time again. So here are some theoretical load profiles. So in higher income buildings, what you see is in the morning, there's a pretty steep peak. The majority of the residents get up, they go out to work, and they don't come home until the evening. And so you see not a lot going on throughout the day, and then you see, sort of a mild peak in the evening as well. As people come back, they might shower, do laundry, cook, whatever. In medium income, the peaks are not quite as high. So as a percentage of the total occupants, the max peak is lower than what you'd see in a higher income. It's also a wider peak, so it ends up going for longer periods. So instead of maybe 7 to 10, it's more of a 6 to 11 or 12 peak. And then in low income, what you have is very shallow peaks, but very long peaks. And so the reason for this is you might have second shift work, third shift work. You might have, people in public assistance housing, so they're not leaving, going to work. They're there throughout the day. Maybe a lot of children, things like that. And so, from a usage per day standpoint, lower income buildings typically have more usage per day, not because the people there use more water necessarily, but just because there's physically more people present in a given square footage with lower income. With higher income, what you see is less people per given square footage, right? So peaks might be higher in the morning because there's more usage percentage wise, but as a usage per day factor, it might be lower. All right, so let's look at the ASHRAE method first. So we've got this apartment building in Manhattan. It's 526 apartments, 16 stories. And you can see, under studio, 1 bedroom to 4 bedroom there, we have different occupancies as far as people per apartment. And those numbers might seem high if you live in other areas that aren't very dense, but in New York City, those ASHRAE numbers that they provide are actually reasonably accurate. 2.25 people in a studio is a lot, but it occurs. So it's 3.5 in a 1 bedroom. Now, if we use, there's the low, medium, high diversity factors within ASHRAE, it should follow demographics, although it's sort of inverse to reality from a standpoint of hourly loads. What we see is, if we took this building and put in the required inputs, for the low factor here, it would recommend a 300 or 3,000 MBH water heater, 5,000 gallons of storage, which gives us a first hour capacity of 7.2 million BTUs of heat, which is roughly 240 GPM continuous flow at a 60-degree delta T. So pretty substantial flow. Now, if you average that out across all of the apartments, it would be each apartment getting half a GPM apiece. With medium income, or with not medium income, with medium diversity factor here, we end up with 5.2 million BTUs of heat required, 8,600 gallons of storage with a first hour capacity of 12.4 million BTUs of heat, which is 410 GPM. With high, right, we end up with 10 million BTUs of heat, 15,000 gallons of storage, right, for a first hour capacity of 22 million BTUs worth of heat. This is a lot, right? So let's take a look and see what reality is. So we went out and did a study of this. We took the cold water flow rate coming into the domestic hot water plant, which basically gives you, what your demand really is. Now, we didn't take into consideration here domestic hot water recirc, but I can add in a factor for that as I talk about it here. So from about midnight to 5 in the morning, there's not much going on. And then the real load starts from about 6:30 to maybe 10:30. And that's what we'd consider a peak load, lasts about 4 hours. Within that peak, there's a narrow peak that lasts about an hour, which is sort of your max that you need for equipment sizing. And then you've got, some things going on throughout the day, but it goes from, 10 GPM to 0 up to 20 to 0. It's very spiky. And then you've got your evening peak, right, which lasts from about 6 o'clock to maybe 11:30, something like that. Now, the temperatures here were pretty consistent. This was done in the summer, but even in the winter, they'd still be consistent. We had about 70-degree entering water. Now, the entering water came into a mechanical room, which was hot. It was a steam plant, so it had a chance to warm up. And then our hot water was leaving about 125 pretty consistently. If we look at just that one peak hour, right, the capacity underneath that curve is 788 MBH. The capacity underneath the curve under that 4-hour peak is about 2.2 million BTUs of heat. And then over the course of the day, it was only 3 million BTUs total. Now, the one thing that isn't factored in here would be domestic hot water recirc. And even at like 10 GPM, 10 GPM, 10-degree delta T, you're looking at about 50 MBH, which doesn't seem like a lot relative to this. But over the course of the day, 50 MBH 24/7 is about 1.2 million BTUs worth of heat. So it does sort of add up on a daily usage basis, even if it doesn't necessarily affect our equipment sizing per se. So because this is winter operation, if we wanted, or because this is summer operation rather, if we wanted to know what winter would be, we'd need to add some factors to safety to it. So this was a university building, and so they claimed that it was fully occupied, but in the summertime people take vacations, and I don't think all the students were there. So we're going to add 15% for full occupancy, and in the winter people are going to take longer showers, so we're going to add another 15% for that. So you might go from 8 minutes to 12 minutes, that type of thing. Also, the delta T is going to be larger in the winter. You're going to have colder entering water, not by a lot, right, because ground temperature is pretty consistent, but enough. maybe 5 degrees. And then your hot water is going to be hotter in the showers, which is 90% of your usage anyways. So instead of maybe taking a shower at 100 degrees, you take it at 105 or 110, something like that. So adding in those factors of safety, the revised peak hour would be 1.15 million MBH, and then 3.3 million MBH over that 4-hour period. So if we look at what ASHRAE provided us previously, right, it was 7,200 MBH first hour usage, which is 2 times higher than our actual peak requirements. If we use the medium factor, it was 12.3 million BTUs, right, which is 3.75 times higher. If we use high, it said it was almost 22,000 MBH, right, just for the peak period, mind you, which is 6.63 times higher than what reality was. And of course, our usage per day, even factoring in domestic hot water recirc, was about 4 million, maybe 5 million in the winter if we want to go that route. So pretty grossly oversized, right? Now, if we take, the winter peak flow, instead of 50, we're adding, 45%, so we end up with about 80 GPM up here. And we sized a heater that could do 80 GPM at a 60-degree delta T. What we'd have essentially is an instantaneous water heater that could handle 80 GPM all day long with no storage, right? So you essentially have an instantaneous heater where you don't need storage, even though you still sort of need storage. Now, the instantaneous demand is 3/4 of the recommended ASHRAE heater with a low usage factor, right? So even at low, they said you needed 3,000 MBH, which in reality, 2,400 would give you an instantaneous water heater 100% of the time with zero storage, right? And the minimum tank size to prevent short cycling with a capacity of this big would be around 500 gallons. You could go a little lower than that, but generally speaking, you want your water heater to have some runtime when it comes on, at 2 in the morning under minimal demand type thing. Now, of course, 500 gallons is still 1/10 the recommended size with the low factor, which was 5,000 gallons. So you can see here that what's being recommended and what you really need are vastly different, right? And this has first cost impacts. This has longevity of equipment impacts. It has impacts due to what is connected to the utility, right? The size of the gas line or the electric line or something like that. So these have real world impacts. So
Bob, you've got 5 minutes.
Noted. Try to talk a little quicker. I'll go New York City speed here. So let's talk about the best place to put a flow meter. I'm going to skip ahead to this a little bit. So, you can put it on the hot water side, but of course, when you do that, you're going to take the domestic hot water recirc flow is going to be measured in there, and you don't want to do that. You could do it on the cold water side, which is essentially right, but you don't want to do it again downstream of the domestic hot water recirc. So the best place to put it is on the cold water supply upstream of the domestic recirc. And of course, it's good to take a measurement of your domestic hot water recirc because that does impact load. So when I go do flow studies, what I do is I put the flow meter on the recirc just for a moment, just to get the full load of that. And then I leave it on the cold water supply for a week. And I take the delta T's at these 4 points. Now, the cold water supply, or the hot water supply minus the cold water supply, right, times the flow rate gives you your MBH of your demand, really. And then the delta T here between the hot and the domestic hot water recirc gives you your domestic hot water load, essentially. So what you can do is basically take those two loads, add them together. If you're monitoring every minute, after 60 minutes, you got your load per minute, right? So pretty straightforward. Now here, is it worth focusing on domestic hot water recirc? So on this example here, it's 338 apartments, 15 stories. I initially measured the hot water supplies, first job I ever did, and it was 150 GPM. And I'm like, well, that's obviously wrong, middle of the evening. So I went back and put it on the cold water supply, right? And it was nothing in the middle of the night, which makes sense. And so what had happened in this building is even though they had domestic hot water manual recirc valves, no one balanced the system. And they had two large ECM motor pumps on there. And when someone complained at 5 in the morning about not having hot water, the plumber just turned both pumps on. And the pumps were oversized to begin with, and this was the result. They were flowing 150 GPM through a building that only required 50 GPM as a max flow rate under peak demand, right? So And in reality, if they had a fully balanced system on the domestic recirc, they could have been flowing 15 GPM, not 150 GPM. So highly overlooked thing done all the time. So what I would recommend is something like the DNG temp setter, where it's a wax activated device in there. And basically you can set it to a temperature between 104 and 150. If it's satisfied, it closes off flow. If it's not, it opens up. So it essentially controls temperature and automatically balances your system. They make them with little bypasses. It's just a manual bypass, so it allows some small amount of flow to come through even when the valve is essentially shut off. And they have it with an electric bypass if you want to control the bypass with the BMS. And then, of course, just an ECM pump back here, which will control off constant pressure. And so as these start to turn down, this thing still, it'll respond accordingly. The bypass, of course, allows enough water where you don't deadhead your pump, which is a good idea. So why are we so oversized, right? So basically, factors of safety get added together. So with occupancy rates, we assume 1.5 times more than what reality typically is. The delta T's, we assume 40 to 140, which never happens in reality, right? It's usually a 50 or 60 degree delta T, so we're 1.65 times higher than what we need. And then flow rates were 3 to 8 times higher, right? And all these factors of safety get multiplied together, so we end up with just crazy oversized systems. So what I recommend is, get sensors, go out there, measure data, build up a backlog of knowledge, and that'll make a lot of difference. And that is it.
Bob, we had no specific clarifying questions, so let's move on to Pete.
Sure.
Pete, got your screen ready?
I do. Do you hear me?
I do.
Great.
Put it on slideshow and let's get going. All right, I'll be in line.
Okay, thank you very much. Thank you, Gary. This is a great honor to be among people like Bob and Todd and Gary. I'm just that little guy from upstate New York, but I've been very fortunate in doing the things that I have over the years, and I'm just going to give you a very short. Let's see, how do I? There we go. Meet guys like Gary who took me in and not only explained how he does the testing of plumbing and fittings, but also make sure that I get on PowerPoints successfully. Thanks, Gary. What I'm going to talk about today is plumbing systems on a small scale, not like Bob, who's doing massive buildings. We're doing low-rise multifamily up in upstate New York, usually 3 stories, maybe mid-rise as well, 7 stories and the like. And I want to talk to you about what we've been coined as practically perfect plumbing, plumbing that's right-sized for the particular application. In my case, multifamily systems that are reasonably sized and are in the vicinity of 24 to 35, maybe as much as 70 apartments. My background includes a lot of experience with water. I grew up on a stream in Vermont and spent a lot of time playing around in water, and then went on to do a great deal of whitewater kayaking around the world. And when I graduated from working in the Attorney General's office for 30 years in New York, doing environmental advocacy, I thought, hey, I want to get my hands dirty or at least wet. And so I might as well do something with solar, because it's always been a passion of mine, something to save the planet and something to keep me busy and do something for people like hot water. So let's see, I went the wrong way here. So I was really very fortunate. I started my business and put in a lot of solar thermal systems around New York. Every one of them were custom systems built from basic principles of continuity equation, et cetera, et cetera. I was trained as a civil engineer. I was not trained as a mechanical engineer, so I didn't know about all this guidance that were available from ASHRAE and ASME and the like. I just went right from basics and built my systems. And when they didn't work, I fixed them and changed them, and eventually wrote a textbook and a whole educational program, which we gave at various sites. And then I got tapped. This is really very lucky. I was chosen by the developer of Net Zero Village. This is the first multifamily low-rise net zero in New York. And Dave Bruns is a real visionary, and he invited other people, and I was one of them, to put in various different parts of this system so it made the net zero goal. And while I was putting in my solar systems early on, I was in the mech room, and the GC and the plumber came in, and they wanted to lay out the plumbing. It's kind of a design build approach. And I said, hey, I've been seeing this stuff on the web about home run, small diameter twig piping to individual fixtures. Why don't we do that? And GC said, sounds good to me. Crunch some numbers and show me it works. And that's what I did. I went back to first principles, figured out what the pressure loss was per foot. And then I recommended, at least did the math and showed that it would work. And in fact, this is what we adopted for all 26 sections of Net Zero Village. This, you see on the right-hand side, the valve manifold with individual lines to each fixture of each apartment. Well, fast forward, it took me about 5 years to get all of those buildings built, and it worked very, very well. Then the owner said, well, I'm going to do another project down the road called Solara. It's going to be eco luxury net zero, and now even embedded carbon. And I want you to design not only the solar systems, but solar thermal systems, but also the plumbing. So I said, how hard can that be? And I went back to first principles and began my layout, and made a very simple layout because simple is good, and made small pipes the basic approach. I didn't know Gary at that time. This is what resulted. On the picture, you see, if you can see, I hope on the left-hand side, you see the 1.25 PEX feed from the mech room in the middle of the building, go to a T with 1.25 going out to each side, which then goes to the red 1 inch with drop-down manifolds that lead to lines that go to 3 apartments in a stack. And if you need to do any maintenance, one valve turns off all the feed to those 3 apartments, and you can work at it quickly and get it fixed. In the back, you see the 1/2 inch recirc lines going back to a pump that I installed in the mech room, and that is operated episodically so that it's 5 minutes on, about 20 minutes off, and that way the trunk line stays within the expected temperatures of 110 to 120. So as I started getting more familiar with how things go, I called up this guy, Gary Klein, and said, hey, I actually did what you said. And he said, great, I'll come out and look at it. And we've worked together for the last 2 or 3 years. It's been great. We coined a term, practically perfect plumbing. And the precepts of it are what the owners want. The owners want controlled installation costs, low O&M. They don't want any tenant complaints, that's for sure. And we want happy and safe tenants because the water quality is good. The tenants want that water to be always hot, free of contaminants. They want it to arrive quick with enough pressure so they have a great shower. And the designers like me, well, we want happy clients, no O&M, and safe water quality. And what does the world want? No waste of water and no waste of energy, and perfect plumbing, right size, gets it down the road. Now, how do we know it's right size? Well, we've got to know what is actually being used. Bob talks about a size that is beyond my comprehension. 1,300 apartments. Oh my God, I wouldn't know what to do, but I do know what to do about 24, 35, 70 apartments. Yeah, it's smaller than he works with, but I have the data now. Why? Because I went out and bought a whole bunch of ultrasonic flow meters. I started early, way back in Net Zero Village, with that little flow meter on the right-hand side of the picture, and started at Net Zero Village and other sites to get more data. Later, we adopted a much more complicated streaming capability. And on the left-hand side, you see Hugh Henderson. He's a wonderful, fabulous metrologist, and he's very well known in New York. And we started by installing these flow sensors and temperature sensors in these facilities to make sure we knew what the flow and the temperatures were. And this is what we found. Here's Solara, 24 units, a mixed population. We have families, we have seniors, we have singles, couples, and take a look here. Down the bottom are several days of data. I picked off a little section of it here to show you that what we saw here is spikes. Yes, there are spikes, and there's some simultaneity here. But look, it's not even as much as 4.5 for very short durations. And as a result, I began to feel much more comfortable with small pipes. Here's another one, Solara B3, 24 units, again, mixed operations. Here, the green is the cold, and hiding behind is the blue for the hot water. But look, 1.5 gallons per minute, except for occasional spikes above that, but they're short duration. And again, at Meadows, this was where out near Utica that we installed some solar thermal systems. And so, of course, I measured the flow. Once again, now this is all seniors, 35 apartments, but you'll see short duration spikes, not much more than 2 gallons a minute. With those data, I began to feel really comfortable with perfect plumbing. Now, I asked my son out in California, he can do almost anything with numbers, to look at the cumulative frequency distributions. And the one on the left is for the 35-unit senior housing at Meadows. And you see, if you look at that red line, it goes up to 99th percentile at 2.63 gallons per minute. The 90% is 1.28. Let's go over to the right-hand side. This plot shows Solara B4. We see a 99%, 4.2 gallons a minute, 99%, and at 90%, 2 gallons a minute. This is for hot water. So this is for 24 units mixed operations. So these are the kind of numbers that gave
Pete,
us. Yes,
Pete, you got 5 minutes.
I know. I'm hitting it. So we went to Beacon Communities. Beacon Communities owns about 20,000 apartments in over 15 states, and they were building some buildings at their Meadows facility. So we looked at the plumbing there, Gary and I, and it looked like a forest of ribs leading from very large trunk lines that went up to the 3rd floor and down. We said we can do better than that. And even though it was under construction, we hoped that they might take our better designs seriously. They did so. We came up with a much smaller line here down the ceiling of the 3rd floor, first floor, I'm sorry, then up to the 2nd floor and back with individual manifolds for apartments, and then a small loop over on the right-hand side. And they were, even though the building was under construction, we convinced the plumber and the GC and the owner that they should scrap that oversized design and take our more efficient, perfect plumbing approach here with 1.25-inch feed that led to a 1-inch trunk line, and then up at the 2nd floor return at 3/4 of an inch. So this is serving 35 apartments, granted seniors, with a lot different demands schedule, but still a very excellent outcome. So I want to finish with something that's really important to me. Trust but verify. Yes, you can trust your calculations, but verify them. We build our own mock-ups out in the parking lot. with the real PEX. It's not very expensive. And we set up our pressure and temperature arrangements there to make sure that we see the same thing happening that we calculate. We check our demographics and the tenant population carefully to make sure our draw patterns make sense. And we look at simultaneity carefully. And of course, Bob, I'm sure, knows about the Super Bowl. Boy, did we see a lot of water use in a very short time. But still, simultaneity was not a problem. It's just that the amount of hot water use is important. Now, the last thing is plumbers make mistakes. They don't read the plans carefully, and they know how to do it the way they always did it. So, in fact, one guy said, when he put in lots of elbows in the PEX, I said, why'd you put so many elbows? He says, because I'm a copper guy. Well, look, we explained to him that this isn't copper and that PEX can bend. And we found out that instead of 2 loops in that building, there was only 1. And the sheetrockers were hot on their tail. But we inspected, we caught it in time, and they were able to split it. That happened again in another building at Solaris. So it can happen, and we need to consider that and inspect what we see. And then before people move in, do a stress test. We did that to show that the pressure we calculated actually occurred at the furthest fixtures, and that the time to tap was right on the money, between 10 and 15 seconds arrival time for all of the fixtures. Short takeaway, the plumbing revolution is here, certainly for low rise, and I'm sure medium rise, the high rise, Bob can talk about. Smaller pipes are in, the fat ones are out. Practically perfect plumbing can save energy, install costs, water, and get that water to the tap real fast. We've made it work. Others have made it work. And we all can help to do a good thing for the planet. And finally, inspect that installation and confirm the performance of the as-built system. Got to do it. It's part of the deal. And I can assure you that I'll answer questions in the far off. Yep.
You have one question that's clarifying. Would you go back to slide 10?
Sure. Let's see. I got to go backwards.
Yeah, good luck with that.
Yeah, good luck with that. What one was that? 10?
10, the 10th slide.
Okay, there it is. Yes.
All right. Andrew Macaluso has a question. What is the time scale?
Scale for this is for these 2 spikes. It appears to be
like an hour. It looks like an hour.
It's an hour, right. So this spike here appears to be about 5 minutes. And this, I believe, these data are they look like they're 2-minute data. But we have so much of these data, we could go on all day. But yes, that's the timestamp.
So what I would observe is that there's a big time scale on the bottom, the tiny blue stuff, and you just took a slice of it to look at one window so you could look inside and see what a big spike looked like.
Absolutely. We've done 30-second data. We've done 1-minute data. We've done 2-minute data. The data caches in these machines vary. And so sometimes if I want a long duration tranche of data, I have to go up to 5-minute data, but generally we look at 1-minute data in our work.
Right, and you've done some work for us out here to do some analysis on the peakiness for Appendix M mathematics, and you've done stuff at 1 second data, 5 seconds, 10 seconds, and we'll discuss that another day. But thank you. That was the only question that I saw for clarifying on the chat. So let's move on.
Thank you, Gary.
We'll go to the next speaker. Thanks, Pete. Todd, I think you're up.
Okay.
Let's make sure everything loads.
So my name is Todd Cook. I'm an engineer located in the San Francisco area. I actually started in building designs in New York City. I've been doing it for 25 years, last 15, specializing in large plumbing systems. So I'm going to be a lot closer to the buildings that Bob was presenting. And I'm going to go through the We Stand Water Demand Calculator, which is the new presentation of how we move away from the old hunter's curve and how we're applying it. What I wanted to start with is a gentleman by the name of Edward Wellman Serrell. He was a civil engineer the mid-19th century, has a long resume. He was an assistant engineer with the 1948 Panama Survey. It was a railroad. It's what the Panama Canal was based on. He worked for a number of railroads. He worked in Canada. He worked in England. He had a long resume. He was considered an expert. In particular, he specialized on bridges. And you gotta wonder, what are we talking about bridges for? We're talking about water systems. But we would note that we have a gentleman who is a well-respected civil engineer, and he was listed even as honorary pallbearer at the funeral of Ulysses S. Grant, and that was because he had started a number of regiments, in particular with engineers, led them, and ultimately he was a brigadier general. So he was brought in as a consultant, and in the article, and this was in New York Evening Post, dated March 21st, 1879, as he reviewed a calculation, it quoted him in saying, in his opinion, the calculations of the assumed strength of the bridge were not accurate. Now, if we were presented with this, we'd say, we better not build this bridge. But aren't we glad that they didn't listen to him when he built the Brooklyn Bridge, or they went forward with it? The point being is, even though we have ways we've traditionally done things, the reality is on the Brooklyn Bridge, there was assumptions made. There's assumptions by very experts made, and it was a stretch at the time. But when we consider that the Brooklyn Bridge lasting today, if you had a chance to walk across, it's a beautiful walk, but it transports many, many cars, many people. What do we learn from it? From our standpoint is we can't always rely on what our opinion, even of well-known experts, are all the time as we design items. Now we get to water systems. In particular, I'm focusing on the We Stand Water Calculator. And going through on the buildings that we are currently designing. I work for a design build firm that specializes in large water systems. We're a union plumbing contractor. I am the licensed engineer. How does it affect our design process? What effects are we seeing on the systems we're installing? And then what are those indirect effects? We know the direct ones on the systems, but what other things get affected by this? Now, the projects we're talking about. These are large multifamily projects. Anywhere from the one on the bottom is one we're currently under design for. It's about 125 units to one that's 250 units, all the way up to projects that are in excess of 400 units. Now, some of those units are 1 bedrooms, some are 2 bedrooms, but we're specifically focusing on multifamily residential for this. And that's where the water calculator is designed for. It's for either single family or multifamily. So as you sat through a previous presentation and said, great, I know I need to downsize. What do I use? How do I downsize? How do I make this decision? Well, this is the one for deciding how much demand water do we have within these types of projects. The design impacts. And if you haven't looked at the water demand calculator, it's shown there. It's a spreadsheet. To give just a little background on there, what that spreadsheet is based on is a similar principle that Roy E. Hunter in the mid-20th century came up with, which was statistical usage of fixtures. But he used really one statistical curve. We have the Hunter's curve that we find in our plumbing codes. This one actually has 4 different ones depending on the size of project it is. What it requires, though, especially in the large systems where we are picking the size of pipes upwards of 500 different sections of pipe. The old way that I would do it is using a spreadsheet, programming a formula, having the spreadsheet run the formula, and then doing a lookup on sizes. In this case, every single section that you're feeding for the number of units, the number of fixtures you have to put in. And I timed myself on doing one, it takes 2 minutes. You start multiplying that out, and a task that perhaps before would take 4 hours may take 3 days to do. It's a more intense calculation. It's just, if you can imagine, I suffer ADHD, it gets very hard to pay attention, but it is increased calculation time. It's a need to be more careful. We talked about oversizing. What did oversizing do for us? Covered a multitude of problems. If you undersized a pump, didn't matter, you never had the friction loss. If you thought you undersized a piece of pipe, that didn't matter, it covered that. So things that you have to take into consideration when you look at your hot water supply, you need to make sure you add their hot water return flow on that. What other design impacts? AHJs. You have to get the approval because it's not fully adopted yet in the codes. There is a push to get it adopted for multifamily, but you have to make sure your AHJ, your plan checker, understands the process. In addition to the way you may in previously just put fixture units on a design, now you have to show flow rates. And the old adage, if it ain't broke, why fix it? Well, the reality is it is broke. We've known it's broke. You've seen 2 presentations on it, but even myself as an engineer looking at these systems, picking a large pump, walking in and realizing of a triplex pump, only one pump ever runs, tells us it's oversized. And so it is broke. But you have to overcome that thought process on AHJ, but also perhaps from a peer reviewer or an architect or an owner. Now, in regards to our systems installed, and as we look at systems, we are talking about our water systems. We're talking about the piping. How does it affect the size of the piping going out? But also, how does it affect the equipment? Bob touched on hot water equipment. That's more based on the total usage. But we do have equipment that goes along with that. Circulation, pressure reducing valves. And I'm talking pressure reducing valves because we do high rises. We may have 3 or 4 pressure zones, and as we get to a zone, we have to reduce that pressure, but we want the equipment to work well. So as we take just an example of a system impact, this is a building that's currently under design, 21 stories, 250 total units, half of them 1 bedroom, about half or 2 bedrooms, there's 2 3-bedrooms. The traditional way of sizing, and we want to note that this has a dual plumbing system. It's got domestic cold water and it's got reclaimed water. Reclaimed water feeding the toilets and irrigation. The old way of sizing gives us 4, and this is uniform code, and we know most of the US is on the international. You come up with similar numbers. 415 GPM for domestic, 225 for reclaimed. If you do bathroom groups, and international code does it well, uniform has a method of doing it, you can reduce that to 340 gallons a minute, domestic, 175 reclaimed. But the We Stand water demand calculator reduces it significantly. You now have 72 GPM domestic, 16, and that's not an error in that decimal. It's not 162, it's 16.2 reclaimed cold water. As a reference, there's about 375 toilets in here. At that flow rate, you can flush every toilet less than a half hour. Repeat that, at 16.2 GPM, you flush every toilet within a half hour. The reality, we don't use fixtures that way. So even the 16.2 is well within. At the 225, you're going to flush them in a significantly slower period of time. What does it do to our piping? Well, our piping goes, traditionally we'd bring in a 6-inch cold water service. we're now to 3-inch. Pull in a 4-inch reclaimed, we're down to 2. And on our distribution, because we will feed up, feed out in, on a floor and feed a group of about 7 floors, that distribution of that set of 7 floors, or about a third of the building, goes to 2-inch. In terms of equipment, we reselect our pumps. Although we will note what typically happens with booster pumps is you do not get a significant improvement. The booster pumps are more affected by head than it is by flow. Our backflow preventers are smaller. And so in the incoming ones, instead of a 6-inch backflow, you're going to 3-inch backflow. And in our pressure reducing valve stations, we look at the performance of those, and our performance gets much better. If I go back, sorry, in terms of if we look at these pressure reducing valve stations, you know, there's curves, and I do have a curve shown on the next one, but as we think about this, if I take a 2-inch pressure reducing valve and I'm only trying to reduce 16 GPM, that valve is almost completely closed. You lose your control. We do on control valves, we have a CV. We want the CV selected right. The reality is we're picking them wrong in plumbing. Now, some indirect impacts. Cities, and this is based on a San Francisco, that particular project I did, it's one in San Francisco. The capacity charges, so when you order a 4-inch meter, what they do is they say, well, we have to upgrade our water system, our sewer system, so we're going to charge you. In this case, it's upwards of $150,000. But if it's really only a 3-inch meter, and in reality it's priced smaller than that, there's a bottom line benefit. This is money that the owner, who's already having, you know, with the current economic situation, having a hard time making projects pencil, has a reduced cost. And when you consider most of the projects we're doing now are for below market rate, for low income, we are dealing with projects that can't afford to go forward because of increased cost on materials and products. We reduce the space, the amount of space that, as if you went through, you looked at Bob's, there was the amount of space hot water heaters needed, but also our pressure reducing. They've taken over the last few years and reduced the height of buildings, which means they reduce the height we have on ceilings, so we can get our pipes in there. It improves the performance of the equipment. Our pumps run where they're selected. Our PRVs run where they're selected. They also reduce the amount of hot water heat lost. When you take your hot water pipe and you reduce the size, you reduce the amount of radiated heat, which will further affect savings on hot water system. When you pick that pump where it's supposed to run and all the equipment where it's supposed to run, we reduce the energy cost. Now, can we say how much? Well, we need to study that. But these are all indirect impacts to why we want to right-size systems. And it is right-sizing. That term's used in HVAC, right-sizing. Don't oversize, right-size it. We need to do the same for plumbing. And the WeStand calculator allows us to do that. Now,
Bob, we're close. You've got 5 minutes.
Okay. What is the next steps here? Well, here's my question. On that 21-story building, which we have a 3-inch water coming in, we have 2 8-inch and 1 6-inch sewer to meet the fixture load requirement. Why? When the table shown R is based on the documentation for cast iron pipes, a 6-inch has a cast capacity of 313 GPM, an 8-inch of 656. Why are we not looking at sewer lines? And that's my presentation.
Thank you, Bob. Why doesn't everybody come back? We can have a short couple of minutes of Q&A among us, and then we'll open it up into the Zoom. Thank you all very much. We have a question that came from John Lansing once Todd got started, for both Bob and Pete. and Todd, you can join in too. Do you have any recommendations of ultrasonic flow meter products for temporary monitoring and data collection for similar studies?
Yeah.
So Bob, you've used some, and Pete, you've used some. Are you happy? Would you change your mind? What do you think?
Yeah, I've used two. So I the one I like and I have, it's expensive, is the Toshiba Portflow C. And it's got an aluminum rail with the ultrasonics that go in it, and that goes up to 6-inch. And there's another one that goes up to like 24-inch that you can do very large pipe with. But that one's pricey. It's like $5,000 for the unit itself, and with all the attachments and stuff, you're looking at about $6,000 or $7,000 all in. There's also an Omicron one, I think, or maybe not Omicron. It's called something else, but it's about half the price, $3,500. But that has a shorter range of pipe. I think it goes from like 2-inch to 12-inch, and then anything below 2-inch doesn't do it. So the Toshiba Portaflow can go from like 1/2-inch all the way up to 24-inch, and you can do any kind of pipe. I've done polypropylene. It can do PVC, stainless steel. It's pretty handy tool.
Pete, I know you've done some.
Yeah, I'm really very happy with the Flexum Fluxus line, the new 700 series device. Yeah, it costs a lot of money, that's for sure. But the data that you get and the data manager are both a tremendous asset, and has been tremendous help for us to better understand the data. In addition, we got, thanks to Hugh Henderson, we gussied it up so that it can transmit the data directly to a server. And Hugh has a data manager there that creates all kinds of analytics that we rely upon. So you can both fill a very large cache in a 721, or you can have a continuous feed into another server for data. And I think, Gary, you've worked on something like that yourself. Is that correct? Maybe you can explain what you've done with yours.
We're trying to communicate with them remotely, and that is currently being challenging. So Bob, are you talking to your flow meters remotely, or are you going to the site and picking up the data on a regular basis?
No, usually I'm doing 1-week flow studies, or sometimes just the day of, depending on what I'm doing. I learned the hard way, though, that you gotta mount those things up high on carabiners and put a rain jacket on them, because the first one I had got flooded in 12 inches of water, and that was an expensive lesson. So subsequent to that, I've done a pretty good job protecting the meters on site. So
cool. Todd, any thoughts on the matter?
A few years ago, we outfitted one with Omicron. We used just a local one because if you go into an existing building, we didn't have access to a internet connection there. As a good rule, and it was touched on a little bit, don't do too many points. It becomes very hard to analyze. The 1 minute per, or even 3 minute per, as long as you do over a long enough period of time. And what we found, and this was a building in San Francisco on an existing 400 unit complex, where they wanted to replace a hot water heater with a cogen. This is one's working at home in a city session. You have people in their apartments all the time. The only time we didn't have hot water use was midnight to 6 a.m., midnight Sunday to 6 a.m. Monday. All the rest of the time there was hot water usage. Therefore, the peak demand was quite a bit lower than what we ever expected.
That just tells us, pretty much all of our expectations about what is actually happening are wrong. We need data to support any analysis. That's one of the key things that all of us have learned. I want to share something briefly with everybody, if I can figure out how to do it, because it's related to this problem of capacity and peak, and then we'll jump over to the Zoom meeting. Well, that's annoying.
Well, while he's working on that, I should also say that we have, I think, 5 different Flexum Fluxus machines. And after I finish the last 3 buildings at Solara, I'd really like to deploy these at a variety of different sites so that I can expand our library of actual consumption data. And I also want to just point out the importance that Todd mentioned. You got to be really careful of where you put these. Bob mentioned it too. The sensors have to be on the right pipes. And what I do is I gather data for a couple of hours and then I look at it, because I say, oh man, I included the research here and I have some backflow there. And rather than leave for a week and come back and find that the data aren't useful.
So my system and I were unable to communicate with share screen. So I would propose that we move over to Zoom and get ready for that, which will happen essentially when we get there. Thank you all so much for participating today. I found some really interesting stuff in all the presentations. Oh, Todd, I do have one specific question. You were showing the calculation at the end about the drain lines. Was that 3-inch sizing based on having used Appendix M to get to the 3-inch? Or was
Yes, so that is with the new WeStand calculator. We've done the reduced usage for water. We haven't done it for waste. And the question is, why not?
Well, like Pete, you have a question. If the flow rates coming in are so low, why are the drain lines so big? Pete's question was, why do we have fat pipe with low flow rates? It's the same question. And I realize there's some disconnect between drain flow rates and water incoming flow rates for domestic, but it's not 100 times bigger. It's 50% bigger, or it's spiky. We don't know exactly, but there's got to be some correlation that we should be able to right size better. And fully agree with it. All right, I'll see you all on the Zoom. Bye, everybody. Thank you so much.